teach astronomy and physics at Jasper Place High School. And for 2 or 3 years now, I run an astronomy class there. There's a lot of reasons why I love teaching astronomy. I'm not going to go into lots of them now because the focus here tonight is on 3 other presenters. But this is about the first thing that I teach my astronomy students. And it's probably one of the most important things they can learn. Aside from that, though, one of the reasons I love teaching astronomy is because of what it says about science education. After the first year of teaching my astronomy course, I gave my students this survey, kind of informally as a way for me to kind of build some evidence to offer more astronomy-related courses. And the thing I found most striking about it was 70% of the students said they're more likely to learn not just astronomy, but any science. Astronomy, in my opinion, is really the gateway to science. It helps us kind of pique our imagination, get us interested in science, and starts to build connections to all the different sciences and why we should be curious in the first place. So this is kind of why I do what I do. This is a great question I'd love to ask my students. This is a map of the solar system, not to scale in terms of distances, but this is the solar system. One of the first things I ask my astronomy students is, we're all taught that this is the order of the planets, but how do you know that? And the interesting thing about this is the order of the planets from Mercury to Saturn was known as far back as ancient Greeks. So we don't need satellites or telescopes to know this, but it's something that we can learn by making very simple observations. How many people know how we, or could explain how we know the orders of the planets? I can't see, I can probably, just think about that. I'm not going to spoil the fun for you. If you want to know the answer to that, you can take my astronomy course, or come and find me after that, I'll tell you. But it's a really interesting question that I think in our modern society, we take a lot of this stuff for granted. We know things, we assume we know them, without really understanding how and why we know the things that we know. So, these are the 3 girls that are doing our talk. They're 3 of my astronomy students, well, 2 of my astronomy students, and 1 girl who's just, I guess, geeky by association. I think they did a fantastic job working on a photometry project that I was so impressed with, I felt should be shared with as many people as we can. Before they came down to do this, I asked them a really simple question, what they learned while they were doing this. And inevitably, some of the answers I got were things like a lot of astronomy facts and information about photometry and variable stars and how it works. But some of the things I found most insightful were what they learned about how they could explain things, how they learned, and what they went about, how they communicate that knowledge to people. Those are skills that I don't think they would have learned in any other avenue. So, without further ado, girls, the stage is yours.
All of us are grade 11 students from Jasper Place High School. So the reason we started doing this project was because we all loved astronomy and we loved learning about astronomy in our class. So we decided to put things we learned into an extracurricular photometry project.
Okay, so we actually started out looking at a star called KIC 9832227, which is an eclipsing binary star with an orbital period of nearly 11 hours. The reason we thought this was an interesting thing to do was because we read in an article that it would produce a luminous red nova. A luminous red nova is a stellar explosion thought to be caused by the merging of 2 stars. But As you can see, it was based on a wrongly timed observation, so we had to go to a different direction.
So we then set our sights on a different star called BL-CAM. What is BL-CAM? I'm glad you asked. So BL-CAM is, there you go. BL-CAM is a SX Phoenicius variable star, which you can find in the constellation Camelopardalis, and it varies by 0.03392 over a period of 0.0391 days, or about 57 minutes. And the changes.
Sorry, guys, video's not going to work.
Okay.
The changes in brightness occur due to radial pulsations inside the star, which cause it to expand and contract as well as change in temperature. So we chose this star because it has a very short period, which means we can take about 120 pictures worth of data over the course of an evening. And the data we would get in those 57 minutes, if we kept doing that over the course of the night, we would get multiple oscillations of the star. Also, BL-CAM is circumpolar, so it'll never set below the horizon in Edmonton.
So Algol was one of the stars we considered doing this project on, but it has a period of nearly 2 days, so it would take us months to actually get a nice piece of data to proceed to get a light curve. So like Angela said, with BL-CAM, we got 120 pictures in just one evening, so clearly BL-CAM was a great star for us to do.
So we mostly focused on the light curve of BL-CAM, which is essentially photometry, and that's the science of measurement of light. We did differential photometry, which is a difference in light variations of the stars being observed. The video you can't see, it just shows that the change in brightness of the star itself gives us the light curve over the time. Mr. Doctor said astrophotography is a great stepping stone for our more science-based astronomy. This is true because we started out in our classroom with our astronomy, and we used our knowledge, our background knowledge, to proceed with this project. So it was related because we had to take pictures of BL-CAM for our data, and we needed to have precise data, so we needed to acquire the image, know where to get the pictures. Also, we had to do image processing, so dark frames, flat frames, to get our data as precise as possible. One of the places we had to acquire images from, one of them, would be Mr. Doctor. There's also Mr. Dr. Brian Martins, who's a retired astrophysicist from King's University. And we also got data from Skynet.
What is Skynet?
I'm glad you asked. I hope you guys get this joke because I don't. Mr. Doctor told us to put it. So Skynet is a worldwide robotic telescope network. They have about 20 telescopes around the world. It's a login website, so you just have to log in and you log in, and you can do you have a lot of settings you can play with. You just tell the telescopes to do observation for you. This telescope is just right outside of Athabasca. It's the one we use. And this is just some of the observations we've done. So there's nebulas, there's BL-CAM, there's a quasar at the really top, and yeah, like Messier objects.
Great, so we used Minuin to find the light curve. Minuin is a software that analyzes variable stars. We wanted a light curve.
What is a light curve?
I'm glad you asked, Angela. A light curve is a graph that shows how the brightness of a star changes over time. So, like I said, we used Minuin to create a light curve. It's a very straightforward software, so it didn't take us very long to learn how to do it. So these are just some screenshots to actually show you how we did it. Just do it First, we created a project, then we added files to that project. Once we got all the files, the first time around when we did this, we just went straight to the light curve icon and nothing really happened, so we were like, oh, what did we do? So the thing we did wrong was we had to go to edit project settings and click on matching and dense stars, because there's so many stars in there, about approximately 1,500, so we had to get them to align. So as you can see here, that around 200 of them align, so that's a good thing. After that, when we clicked on the light curve icon, it brought us to this page where we had to pick the three things after, I can't see what they are, and the right ascension and declination. We already had the right ascension and declination from the FITS files we got from Skynet, but like, if you didn't have it, then you can put it in manually. After that, all we had to do is click the lowest aperture, and then we get this, where we had to pick our BL cam star and comparison and check star.
So the red star is BL cam, that's our variable star. And the star in green is the comparison star, which is the star that we are comparing BL cam to because we're doing differential photometry. And then the blue star is the check star, which basically just checks that the comparison star we selected is a non-variable star. So to find the star that matches up to BL cam, we needed a star chart, which we got from the AAVSO website. So it was very simple. All we had to do was put in the name of our star, which if you don't have the name of your star, you can also just put in the right ascension and declination. And you can use this. You don't have to use this for photometry if you need a star chart for any reason. This is a really good place to find one. So this is the star chart we got. You can see BL cam right in the middle there. And all of it, you can probably see the numbers on some of the other stars. Those represent their brightnesses. And all of those stars are known as non-variable stars. So they're excellent stars to choose as your comparison or check stars. So once we had our star chart, we now had to do what's called plate solving and find BL cam in this image that we got from Skynet. So the first thing we noticed is that this really bright star matched up with this one, and from there we noticed that the image we got is actually flipped. And once we figured that out, it was actually really easy to find BL cam. We found these three stars, matched up with the three stars right there, and from there we were able to determine that BL cam was right there. So yeah, you can see how we matched the stars.
This is one of the first light curves we got. The data points we got from here are from Skynet. The first thing we did was find a curve fit for this graph. As you can see, there's a lot of gaps between the data points, and that's because Skynet sometimes just observes something like gamma ray burst over our observations. Or also, this over here is over a period of this is about an hour. So within that time, maybe the weather was not permitting observations. So that's one of the reasons we have gaps between our data points. So much so, we were actually pretty happy because this was our first time around. I'd like to focus your attention to the y-axis over here. As you can see, this just represents the brightness change. So it goes from negative 0.85 to negative 1.15, which is about a variation of 0.35 magnitude. And this was our second time around. It looks much better, and these data points we actually got from Mr. Doctor. There's multiple oscillations which looks nicer. And it's also easier to work with because we can fit a better curve fit for this graph. Another reason, if you look at the y-axis here again, the magnitude variation again is 0.35 magnitude. And this was the last time around. This was by Mr. Dr. Martins. These pictures were taken in different night over a span of a couple months. And the period of BL Cam is supposed to be consistent, and the fact that when we did our period solving, we got a consistent period, shows us that we did something right. And to find the period, all we had to do was go from one node to the other, and just a simple math, and then we found the period. One thing though, since we were doing differential photometry, we wanted to make sure our data was accurate. And if you can remember back to our comparison at Checkstar, they shouldn't have a variation in light between them because they're non-variable stars. So if you look over to the y-axis now, it's way less. And doing math and stuff, it's 20 times less magnitude change than our variable star. And the slope of this graph was 0.0035, almost horizontal. And this shows us that our data we had was minimal to like really close to accurate. So our period, we ended up actually getting approximately 63 minutes, and the actual period is 57 minutes. We were actually very happy with what we had got because we didn't really think we would get that close. I was really because since we did everything by hand, it was really prone to human errors and little mistakes, but getting really close to that, it felt really nice. It motivated us to do something more. And this is just a cosine equation that we made up for one of the blood curves. It looks really nice. So, and then after we got the period, that was the goal, we got the period. It made us really happy because we were really close to it, and then it motivated us. It was more of a boost. It's like, wow, we really did that. Because honestly, going into it, I knew that like the period was really short, but I didn't know exactly how short. So once I did the calculations, I went to Mr. Doctor, and he's like, "You guys actually got close," and it's like, "Whoa, what, really?" So other things that we are interested in now is like maybe observing in the nova that might actually happen, or our knowledge from astronomy that we want to further, because in our school we're looking into having an astrophysics class. There's also possibilities of looking into observing exoplanets, and this project has motivated us to just do better, and that's it.
Well, thanks. That was really good. Is there any questions? Hang on, we'll bring the mic to you.
Thank you. I'm just curious, what causes the variability of BL Capital Pardalis? Why is it a variable star?
Explaining that's a lot more astrophysics than we have learned. Like that's kind of a little over our heads. Basically, as far as we know, it is expanding and contracting, which as it expands, it cools, and then as it contracts, it gets hotter. And as far as we know, that is what is causing it. But we don't know a lot of the in-depth physics on that.
What do you want? Mr. Doctor, what do you want?
I know, we
He loves to talk about astronomy, so keep it in mind.
I'm pretty comfortable right there.
Yeah.
Okay, we got one over here.
Yeah, I'm curious, how did you make the actual measurement in brightness on comparison? Did you tell?
Oh, we just put it into Medium, and it kind of did the calculation and everything for us.
Oh, so it did,
You speak
it
into the
looked
mic.
at the
Oh,
data,
I'm sorry.
it looked at the real-time data, the image you had and compared compared it to the comparison stars and came up with an answer? Okay. Okay.
So this is the second photometry project, so I don't want to interrupt you. This is the second photometry project I had students do. The first one we used a different software, but the basic idea is the software takes an image and it counts the number of each pixel, and counts the well depth from it, and then it just kind of sums all of them. So the first software I used, you have to do that manually with each star, and then UniUA will kind of automate that process. So you just, once you align all the stars as the fields line, and then it just adds up the brightnesses for information.
Thank you very
Does
much.
that answer your question?
Yes, it does.
Thank you.
Over here.
Yeah, this is for Mr. Doctor. I'm a Libra, and the stars and planets have affected my life in a very profound way.
I'm sorry, was there a question there?
I'm a Pisces.
Did you make any effort to explain why you have a difference in your calculated period and the official period? An explanation for why there's a difference?
I thought, our only explanation was that we did this by hand, and maybe when we did the curve fit, the data points that we chose to be in the curve fit mostly weren't the best ones to pick. Also, there's 3 different graphs, so when we did one for each, I guess, the difference. Okay, how do I explain this? It was basically because we did this by hand. Maybe if we'd used a computer program to find the curve fit for all the data points to be included, maybe it would have been better. But we did this by hand.
So you don't think there's a physical reason why there's a difference?
You tell us.
No.
It doesn't work that way. That's why I asked the question, to get you to think.
I have a question now. How many courses did you take, or is this one course?
Just one semester.
And what grade is that?
We did a grade. Oh wait.
There's people at all grades in our class. Yeah.
Wow.
Taken science 10.
Okay. Cool.
One more? Maybe more?
This is more of a comment than a question, but I've read in the Facebook article that he got shout out from the researcher of KIC Star, and I don't know if that was you or some other student, but no? Oh, okay. Sorry.
Any other questions? I'll be there next.
It's great to hear from you all. It's fantastic. So each of you, what kind of things are you interested in pursuing next? In terms of what you talked about, exoplanets and other things. Have you got some pet projects you're interested in?
That depends on Mr. Doctor, because you kind of introduced us to this, so we don't actually know what we want to do next with this.
One thing we do want to do is our school, we have an astronomy club, so we want to inspire other kids to be like, whoa, these are actually opportunities within our school. It doesn't have to be all school-related stuff, it's just your hobby and it's for fun, right? So even though we don't know what our exact project's going to be next time, we just want kids to know there's opportunities in our school that you can explore and have fun with, not just about school and grades.
I have a question about, do you have any visual astronomy sessions too? Do you have any visual astronomy observing sessions?
When we had astronomy, as a class, we had to go outside and do star days. Is that what you're talking about? Yeah. So we had projects where we'd have to observe some stars, and we had a whole sheet, and then you come out one evening, and then you just observe them, and you learn how to use telescope and learn how to learn how to observe stars. Sorry.
Cool.
Lots of good questions.
So my understanding understanding is that you did this in your spare time for fun, and it seems like an enormous amount of work. What was your favorite part of working on this project?
My favorite part was just learning kind of like how science happens. Like, we never get opportunities like this in just a regular science classroom. So that was probably my favorite part, just actually going out and collecting data and then just learning how to do that part instead of just kind of like learning and memorizing. It was very different. It was really fun.
Sure. Kind of the same thing as her, but I was actually not in their astronomy class, so I didn't really know anything about what we were talking about, or variable stars, or what a variable star even was. So I guess I got to learn a lot of new things about astronomy. Yeah, that's pretty much it.
When we started this project, it wasn't for the presentation today. It was just, we're just gonna do a project. And what happened was, we like meet over like Mondays, lunchtime, and then we're just working on an article to like write about BL Chem. And then the opportunity came up. He said we should do it. We were crazy. We said yes. And then it's just, honestly, it's just the growth of like going from nothing and then being here today and then presenting it for everybody. That's what I've learned.
I just have one more question. Would you be interested in a free membership to our club for a year? We're giving some away to deserving students. So I'll talk with you later. I just need your parents' email address, and we'd be happy to award you with that gift. Congratulations.
Anybody else? We were actually talking about that at over dinner. Okay, well, thank you very much.